So, basically in logic we will be concerned with how a proposition follows from a set of other propositions. So, we have to formalize what is proposition, what is the meaning of follows of, and so on. All these things we have to formalize specially. Then we start with what is a proposition. If you say a proposition, we are not going to analyze further, we are not going to be looking deeper what is in a proposition, like your grammatical things, subjects, predicates, and so on. We are not going to do that. We will be starting with the propositions, right. But then it should be very simple logic of propositions as usual, something is true, something is false, and so on. And where is the need for formalization? Why do you need to precisely formulate it, right? So, let us see an example. Say Jack likes apples, or Jack does not like apples. And Jack likes oranges. Consider this proposition. From this, what do you conclude about Jack's liking for fruits? He likes apples, oranges. Yes. Now you have to decide. Well, suppose I think of this way, right. Now I can say yes, Jack likes oranges, because the first one within those two parentheses I am not bothered about it. It is anyway there, it does not matter, whatever it is it right? But suppose instead of this I do it this way. What does it say? Is it definite that he likes oranges? So, we need precise formulation. Is it clear? We will use some sort of thing, some punctuation marks like parentheses, right, and we will not always write all these propositions, the basic ones which are involved in detail. We will also symbolize them. Okay. So, we will start with our symbols in this form. We need the punctuation marks, left parenthesis, right parenthesis, and we may have some connectives like your or, and some others, even not. Okay. So, let us have some connectives. You can have other connectives, there are in our languages, but I am not telling what do they mean, right. So, you do not know what are they, we are just introducing some symbols. You can read them, but you will say how to read them, what is their meaning, maybe meaning will be later, but reading we should have now, otherwise it is difficult to write something and not read it, it will be difficult to work out. So, let us give some name. This is called negation. First symbol is called negation, which you may read at not, its meaning will be something like not later. Then this symbol, which is a wedge, it is called a wedge also. So, we will read it as all conjunction, or rather we will have a name as conjunction, we will read as and. Okay. Then this symbol which you write as V in LaTeX. So, we will give a name to it as disjunction, and we will read it as or as usual. Similarly, this one side arrow, right arrow, so we will give a name. So, call it conditional. You can read it as implies, arrow, or if then, somewhere, but nothing is so precise there. Conditional is the best. Let us read as implies. Fine. Last one, which is double arrow, will give a name biconditional, and we can read it as if and only if, or if. So there was something like, you can say it is as fif, it is from if this way and the phi this way, right. So what we will use IFF, this is traditional again to write IFF, not FIF. Okay, so these are the symbols we are introducing slowly. There are some other symbols like which will be our propositions. We have top, we have bottom. So read them as top, bottom. Okay. Next, we will have some list of infinitely many symbols now, P0, P1, P2 and so on. So these are called atomic propositions. But we will give a different name, we will say these things as propositional variables. So these will be called as propositional variables. And both these together will be called as atomic propositions. So we are just varying a little bit, but it will be useful for us. So in that sense, these two symbols are called propositional constants. Okay. So it is something like telling Jack is a name. Okay. Then you say good is an adverb or adjective and so on. We do not know what is the meaning of noun or proper name or adjective, we are just giving some names, right. So we are going to define a grammar, that is how it will be precisely formulated. Okay. So all the symbol we are going to use are given here. They will be punctuation marks, left parenthesis, right parenthesis, connectives, these 5 connectives, and then propositional constants, top and bottom, then propositional variables, P0, P1, P2 and so on, right. All these together is our alphabet of the language. Just like in English language, you have the alphabet which contains the symbols A, B, C, D and so on, but every string is not a word. There are some strings which will say they are words, they will be found in the dictionary, others are not words. Okay. The same way, but there is a difference, the natural language grows, it includes something, here nothing will be included, static, once defines, that is it. So now we are going to define what those particular strings are where we are interested, fine, and we have to take care of that example. No malformation is there, it should be well formed, so that we can assign meaning later. Okay. So how to declare the grammar now? It is done in a very cryptic way. For example, your Bacchus-Naur form, we can say all the propositions are generated this way. If you look at the grammar, it is so simple as this, only one line gives the grammar, but to read it will be more difficult. That is the reason we have written it very cryptically, but once you are acquainted, it will be easier to write it in this form. Here what happens is first three things top, bottom and pi, they are from the alphabet. Okay. So, there is nothing to worry about it, we know what they are. The problem comes when you read this symbol, not W. It says W can be not W, right. That is the cryptic thing. In fact, every instance of this W can be different, that is what we have to remember, right. So, you can read it the other way. Let W stand for any proposition. Now, start reading. So, any proposition can be top or bottom or a propositional variable or negation followed by another proposition, not necessarily same W, okay, or a left parenthesis, a proposition and another proposition, a right parenthesis, or now you can read it. That is what it means. So, when you write it in terms of formation rules, you may have to write 4 or 5 sentences, but let us write it to make it clear. So, it says something like this. A proposition can be top or bottom or a propositional variable. So, in another way you can tell it, you can just declare it like every atomic proposition is a proposition. That is another way of writing the same thing, okay. Because top, bottom and propositional variables, all of them are called as atomic propositions. So, next we have to take care of the connectives. If X is a proposition, then not X is also a proposition. Now, you can see its translation in the grammar, W can be not W, that is how we have to write it in English. Then all the other things we can write, if X and Y are propositions, then X and Y, X or Y, X implies Y, X if Y are propositions. Then there is one more rule which I am not writing here, but we must remember, that is the FR4, formation rule 4, which says nothing is a proposition unless it has been generated by application of one of these 3 rules. We just close there, nothing else is a proposition. Unless you declare it, you may say yes, something else is also a proposition. See, there was once a lecture going on in logic. So, one person wanted to convince the students that there is something called non-monotonicity in our arguments, right. Monotonicity means if you have some assumptions, you have concluded something from it. Now, if you take different assumptions along with the earlier assumptions, the earlier conclusion still is a conclusion, right. That is monotonicity, but that is violated in some cases. To show it, he has presented some argument and then proved that a cow has 2 legs, right. It is coming because you are not following non-monotonicity, you are monotonically arguing, that is why this is happening, a cow has 2 legs. Then there was a student there who just answered, yes, a cow has 2 legs, is it not? Now, the intention is it has 4 legs, so it has also 2 legs, it has also 1 leg, right. So, we do not want such things to happen, that is why we need a closure rule, nothing else is a proposition unless it has been generated by applications of one of these rules. Okay? We are not writing it, but it is there implicitly. So, now I think you understood what is the meaning, how to, not meaning exactly, how to generate a proposition starting from our alphabet. Not every string is a proposition, but the strings which are in these forms alone will be considered as propositions. Okay? But the definition is in a sense recursive, okay, like your definition of factorial function, right, not as a product of from 1 to n, but n factorial equal to n times n minus 1 factorial, okay, because it uses the word proposition again, right. So, it uses the symbol prop, where when you read x and y are propositions, it means if x and y belong to prop, then x and y with parenthesis belong to prop. So, that prop now as a symbol is being overused. So, it is recursive, but we see that it is not ill defined, it is recursive, but well defined, right. Well, what we want is not only this well definedness, we want that there is no ambiguity, because finally we have to resolve whether it is this bracket or it is this bracket, that we have to resolve. So, that means the brackets itself, the parentheses themselves should tell which one we have taken, we should not have to insert the new parenthesis, right, it should not be ambiguous, that is our aim. So, we will go slowly towards that, fine. Once we do that, then our syntax will be complete, we can go for giving meanings, we can connect to the reality. This is our thought now, okay. It is not in the reality, we have just created the symbols, and now we have to play with the symbols to bring to a certain place where there is no ambiguity, that is our first concern. So, let us see how a proposition is generated, whether some any string is a proposition or not. Say I start with top implies bottom, is it a proposition? Yes, it is not a proposition. If it is a proposition, tell me in which way we have generated it. Top is a proposition, yes. Bottom is a proposition, yes. Then it is not a proposition, right. So, I can generate a proposition with the top and bottom the same sequence, but with parenthesis. Without it I cannot generate by following the rules of the grammar, fine. Therefore, this is a proposition, but this is not, right. I can say P1 is a proposition, okay. What about this? It is not a proposition, right. Once there is parenthesis, there should be some connective, not the negation, the other connectives. So, let us give a name, we call negation as negation or a unary connective, others are binary connectives, because they always take two things, right. So, we need a binary connective whenever there are parentheses, there is no connective here, why binary connective? So, this is not a proposition, okay. Is it a proposition? Well, if it is a proposition, then my next question will be, show me how you have generated it. If it is not a proposition, then what should be my next question? Huh?
How do you show it's not a proposition?
That is a tricky thing to decide. Huh?
If we can show it to be ambiguous, then maybe
So, you have to decide something on ambiguity. When do you say it is ambiguous? There is no meanings yet.
If you assign some constant value for the propositional variables, if the overall proposition can take,
That is giving meaning.
if we can add parenthesis and make a proposition. then this is not a proposition.
Then it was not a proposition earlier, right? Well, that looks all right, but where to add? There can be many ways of adding. Any one will do. It is a non-deterministic algorithm now. Huh? There is a complicated thing, right? Well, let us start with a proposition and see how does it go. This looks like to be a proposition. Let us try to find out why do you say it is a proposition. Yeah. So, I could have started this way, say P2 is a proposition, okay, by FR1, P3 is a proposition again by FR1, then P2 or P3 with parenthesis is a proposition by FR3. Okay. So, let me write this on the top of it, I say P2 or P3 okay. From these two propositions I have got this proposition applying formation rule 3. Is that okay? Next what I do? I take P1 as a proposition, therefore not P1 is a proposition. Since these two are propositions, I can use implies symbol and get a proposition not P1 implies P2 or P3. This is a proposition. Now I know that P0 is a proposition, therefore the original one given is a proposition, right. Now I can see it as a tree. Yeah. So this is the parse tree of the string that is assumed to be a proposition. Now given a string you can parse like this, and you see that this is the only way of parsing it, there is no other way you could have formed it, right. But if it is not a proposition, what is happening? Let us come back to what you told, it is not a proposition. What will happen here if you try to parse it? So you must see what is happening in parsing to proceed. Let us again go back, try to see what is happening in parsing. To show that this is a proposition, we must find that the left one, that is P0 is a proposition, the right one is also a proposition, the left right of connective implies, right. So it is really unfolding the formation rules slowly. When you form it, you form this way, starting from the atomic propositions here P0, P1, P2, P3, right. But when you parse it, you unfold the other way, and that makes it difficult in the parsing. It is a tricky affair, because you have to first find out which one was applied last, that is to be unfolded, fine. So let us try to find out which could have been the last application of a formation rule, fine. So that means in order that it is a proposition, it has to match in one of those forms, right. It will be top, bottom, or not of some proposition and so on. Which one it can match? It is starting with a parenthesis. So FR3 must have been used at the end. Now if FR3 has been used, what could be the connective? Now you can see, if you start from left, you get this as the connective. If you start from right, it can be this, considering this parenthesis, right. But that is also tricky, it is recursive. First we have to show this itself can be taken as a unit, then only you can come to this, fine. Okay, keeping that to heuristics, let us try to see it from the left. If I see it from the left, we can parse it with this as the connective P0, and the other one is P1 if not P2 or P3, fine. This is an atomic proposition, so it ends there. Now we come to this place, here I cannot parse it further, right, because this is neither an atomic proposition nor starting with a left parenthesis, so nothing can be done. I stop there, right. Now if you have taken this one as the connective, you would have got a different tree, right. So it would start from this way, where one will be P0 implies P1, the other one is with parenthesis not P2 or P3. So there are really two parse trees here, none of them is giving a proposition at its leaves, right, all the leaves must be propositions in order that parsing is correct, fine. So there might be ambiguity in parsing, or even if you parse it, it can have a leaf which is not a proposition, then you say it is not a proposition, okay. Is that clear? So you can write an algorithm now to determine, given any expression from our alphabet, given any string over our alphabet, whether it is a proposition or not. Yeah. Can you write? See, all that you have to do is identify which one is a proposition inside it somewhere, fine. You could have started identifying this, say not P2 is a proposition because P2 is atomic. So now this not P2 I can forget, write is some P100 instead of it and proceed, right, because all that we do in parsing is unfolding the formation rules. So now once not P2 has been accepted as a proposition, P2 should have been accepted as a proposition, P2 is because it is atomic. So you can start the other way, see P2 atomic, identify not P2, then think of that as a proposition. So replace not P2 by something else, say P2, does not matter, you do not have to invent symbols, fine. Now if you do that, what happens for this? Okay. Any other bracket, one more parenthesis. So what we identify is one of the substrings of this is in the form not P2. So this not P2 I can replace with P2. So now I get, after the replacement, now there are connectives and I can find out which connective I should take, so that it will become unified with one of our rules, that is important. So I can take this one as an atomic and the other one is also that, but it is may or may not be unified, provided the other one is also a proposition, right. So I will not proceed that way, I will proceed with a substring which matches with a proposition, right. So I will identify this one which is a proposition, because P2 is P3 is P2 or P3 with parenthesis is, then I replace that with P2, okay. Now my algorithm stops there, because this whole expression cannot be identified with any of the propositions. If I take P1 here implies here, then the whole thing should have been a proposition, right, but it is not. But to make the algorithm better, not depending on finding out whether this is a proposition or not, what you will be doing? You will not stop here, you will proceed thinking that this is also a proposition starting from the left, right. Okay. So, we will be continuing this way, say P 1 is 1, this is another. So, this should have been some x, but it is not a proposition, that is why we cannot take that way, you have to stop here. In order that one rule will be applied, each one of these two components should have been propositions. This is a proposition, but this is not. So, no way, algorithm stops there. So, it looks that this procedure can be used to determine whether any given string is a proposition or not. Okay. Just go on replacing by following the formation rules. But then what really allowed us to proceed this far? There are some properties in a proposition which this allowed, otherwise we would not have come to this stage. So, the first property there is left and right parentheses are matching in any proposition, that is easy to see. Is it okay? Can you see that? Take any proposition, number of left parentheses equal to number of right parentheses. Yes, or you need a proof for this? Take an example first, see whether it is all right. Now, proof will not be difficult, because a proposition has been formed by using the formation rules, and in each of the formation rules you see matching of the parenthesis is there. Therefore, whatever you get from this recursively will have the matching of parenthesis. So, the proof is by induction, a formal proof is by induction again, because every step you are increasing the length of the proposition or the string. Okay. So, I left it here, but we note it down as a property of propositions. If W is a proposition, then the number of left parenthesis equals the number of right parenthesis in W. Okay. It is an easier property. Next property is a bit difficult, but you can still find it out. You consider a proposition, look at the example we have already worked out. Read it from the left, take any prefix of it. Okay. Do you see something is happening there? Well, tell me about parenthesis.
It's matched first. Total is first matched.
Totally is matched, that is fine. I am asking about the prefix of a proposition.
Number of left is always greater than the number of right.
Can you see that?
They are equal.
Yeah. Is it strict?
They are equal to.
Huh? Greater than or equal to is fine, but is it strict? Is it greater than always?
Yes.
If it is a proper prefix, right? Because the prefix can be the whole string also. Prefix means you are reading it from the left side, stopping at somewhere. If you stop only at the end, you get the whole, right? There you will have number m, but before that number of left parentheses must be bigger than number of right parentheses, provided there are parentheses, right? You can have only negation symbols and then p I, is it right? So, you can have an example of a proposition like not p0, there is no parenthesis, you take any prefix of it, you will get only nots, any proper prefix. Is that clear? So, now how do you formulate second rule? It is about the prefix of a proposition. Yes, if u is a prefix of W and W is a proposition, then what happens in u? U can be what? we are talking of a proper prefix, right. So, let us take u is a proper prefix, then what happens? Yes. So, that means u can be empty string, that is one triviality we have to see, or u can be a sequence of knots equal to only a sequence of knots, right, or number of left parentheses in u is strictly greater than number of right parentheses in u. Is greater than okay. Now, if you do not take a proper prefix, then there is the other possibility that u can be equal to w, right. So, let us remove this and make it proper by removing this proper, or u can be equal to w. Is that okay? In fact, this last property can be formulated in a different way. You can just say that if u and w are both propositions and u is a prefix of w, then u has to be equal to w. It is slightly cryptic. Okay. If you take both u and w as propositions and u is a prefix of w, then u has to be equal to w. No proper prefix of a proposition can be a proposition. This is what it says. Is that right? So, you can utilize these properties to prove that our grammar is unambiguous. Okay. So, now what is that we are going to prove? Let us formulate it first. Our grammar is unambiguous. That means, if a proposition has been formed, then its parse tree is unique. It cannot have a different parse tree than what you have got already, right. So, this means if a proposition has been formed, then the way it has been formed is the only way it could have been formed. Is that okay? So, if a proposition is already formed, there is only one way you can read it. All these things tell the same thing. That is why the theorem you are going to prove is called unique formation theorem, unique parsing theorem, or unique readability theorem, whatever way you want to look at it. Fine. So, let us state the theorem first. It says each proposition is uniquely parsed. Take any proposition. So, proposition means it is a string over the alphabet having possibly some parentheses, some connectives, some propositional constants and some propositional variables. It is a finite in length, right. If you count the symbols, it will be finite number because they are strings. Now, you say it is a proposition, means all the rules have been applied, not exactly all the rules, right. Only some of the rules could have been applied, but only from those rules we have applied some. Then after application you have got another string that string is your proposition. Now your concentration is on that particular string what you have obtained. Now you say the way you have obtained it is the only way you could have got it, no other way the same thing could have been arrived at, right. So, what is the meaning of this way? The way you have obtained it means what? Means you have identified from the atomic propositions which one to choose, top is there, bottom is there, P0 is there or P100 is there, how many P100s are there and so on. First step is that you have chosen the atomic propositions. After choosing the atomic propositions, you identify their occurrences. So, this is my first occurrence of P0, this is second occurrence of P0 and so on. In an order it has been written. Then you combine which one with what, using which connective, that combination is done. After the combination you go to the second step of combining the newly obtained ones with the old ones or all the new ones and so on. Slowly you continue. That is the way you have obtained. Now you are going to say that that is the only way anyone could have obtained this proposition, nobody else can obtain it in any other way, right. So, here if you define or look at the set of propositions in a different way, it tells you the meaning of this way of obtaining it. So, we could have defined propositions in altogether a different way instead of the formation rules, right. Our formation rule 1 says that all atomic propositions are by definition propositions. So, we write that as prop 0 without any connectives, right. Then we go to prop 1 which will have at best one connective, right. Then prop 2 including prop 0 and prop 1 you put another connective. So, you can really generate that way, is it fine? So, let us see it that way. See, I can define prop 0 subscript 0, let us say, okay. This is equal to top, bottom, P0, P1 and so on. Then I can say if prop I has been defined, okay, we can change it prop I plus 1 equal to prop I union, something will be generated basing on elements of prop I, not x, or you can say x and y, or you can say x or y, or x implies y, or x if y, such that x y are in prop I. Okay. So, we are generating is level by level. So, this I here indeed gives you the depth in that parse tree. Can you see? So, the leaf level will be covered by prop 0, go to the next level, that will be covered by prop 1 and so on. So, that gives you the depth. Then finally, you say that prop or the set of all propositions is equal to union of all these. So, recall n is our set of natural numbers including 0. Okay. So, this is what you are doing when you do parsing, you are doing it level by level in the trees. So, this is also another alternative definition of prop, but it is required to be proved. Again, proof will be by induction, that what you generate here is a proposition, and then from the other side every proposition is there in some level, right, because it is finite, that also can be done. Fine. Now, what about the proof of unique parsing? So, you have to think a bit, right, see how to proceed with this. So, what we have done till now? Yes, one sentence I want. We have simply defined what prop is, right, we have understood what unique parsing is.